Well, a very good afternoon, ladies and gentlemen, and welcome to our third lecture of the day. Remember, if you do miss a lecture live, you can always watch it on your interactive television system in your room. If you need any help accessing that, your sweet stewardess will be happy to help. I am thrilled to introduce you to our third lecturer today. He will be with us, of course, for the entire voyage as well. After spending 30 years with NASA, he switched over to the International Space Station, and now he works in the private sector. He will tell you all about himself, and he's got a lot of information to share with you. So without any further ado, please welcome Frank Buzzard.
Thank you, Heather. How's everybody doing this wonderful, beautiful day on the Seabourn Odyssey? My first time on the Odyssey, and it'll be wonderful meeting you and speaking to you. Most of what I will say to the next couple of lectures will go over my head. Don't feel bad about it. Catch me at dinner, and we'll go from there. And the other thing I would like to do, the only fashion statement that a man gets to make is what? His tie, right? So you will see that I will have some ties to show you. This is my first offering, and it includes the Hubble Space Telescope and the space shuttle below it that we use to take the Hubble Space Telescope into space. Now, I have a series of 3 lectures now that use Hubble photos. We are very, very visual people. And photographs from the Hubble Space Telescope have revolutionized our understanding of what we call cosmology, or the cosmos, or the universe around us. So what I want to do is take you on a little journey that starts with the big picture. Any of you old enough to remember that TV series, The Big Picture? Okay, several of us. Probably you watch the History Channel now, like me? Discovery Channel? Okay. So we're going to do the big picture, which is the realm of the galaxies. Then the next lecture, I'll bring you into our Milky Way, which is one of billions and billions, Carl Sagan imitation, galaxies. And then the third lecture, I will bring you inside our solar system, and including some recent findings of Pluto and its large moon Charon from a probe that we sent 10 years ago. Pluto is so far away, our largest rocket, swinging by Jupiter, the probe, at the highest speeds ever achieved by a human spacecraft, took 10 years to get to Pluto, and it went by this year. So with no further ado, if I may, let's get started, and we will talk about the realm of the galaxies. Now, why would we want to put a telescope in orbit about Earth? Anybody?
No dust.
No dust? That's a good one. What else? Why do stars twinkle? Because we can. That's a good answer. Atmosphere. The atmosphere is constantly moving. It's like a boiling pot of liquid, only you don't see it boiling with bubbles, but it has density differences that cause the light from stars to be refracted. And if we get outside the atmosphere, those stars are bright pinpoints of light, and we can take extraordinary photographs. And in 1990, we launched the Hubble Space Telescope on the shuttle Discovery. I had the great privilege of being part of the launch team for all 5 of the 6 Hubble missions. Later, I started in navigation, guidance, flight control, trajectory design, software, system engineering, and then while I was in the system engineering part of the shuttle program office, I was part of the launch team, and of the 126 shuttle launches, I was at approximately 80, and then moved on to the International Space Station. And it takes a big team to launch something as complicated as space shuttle. So we launched the Hubble into orbit. We opened its sunshade. We have a sunshade so that we never point the telescope at the sun. If we do, we will cook the mirror and the optics, never point it at the sun. We took our first picture right here. Terrible, terrible day when that picture was downloaded because it was all fuzzy, and we missed a ground test to save several tens of millions of dollars that would have pointed out that the mirror was ground in the wrong shape. Very, very tiny, tiny error, but enough to make what should have looked like this, a picture of a galaxy, came down looking like this. What we did was we put together a team of the Goddard Space Flight Center in Greenbelt, Maryland, and the Johnson Space Center south of Houston. And in 2 years, roughly, we basically took the information from this and then did ophthalmology on the Hubble Space Telescope, and we built a large box the size of a refrigerator that acted like contact lenses to correct this tiny, tiny error. And once we did that, our astronauts went up, we rendezvoused with the space shuttle. The Hubble Space Telescope was always designed from the beginning to be able to be serviced by the space shuttle, and that allowed us, over its 25-year history now, to constantly upgrade its instruments and to constantly make it a better performing telescope. And I believe all future spacecraft will be, that aren't somewhere where we can't get them to them with a space shuttle or some other vehicle, will be designed to be revisited, refueled, and refurbished. A word chart, don't worry about it too much. These are the different types of launches that we conducted on the shuttle, and some of the things that we did. We fixed broken instruments, gyroscopes in this case, sensors. We replaced the solar arrays. We found that early in the launch of Hubble, it goes in and out of sunlight every 90 minutes. So it has what's called an eclipse as it's going around the Earth. The temperature change caused the solar arrays to flex, and that caused the spacecraft to vibrate slightly. And can you imagine a vibrating telescope? Do you think that's a good thing? That's not a good thing. So on one of the missions, we designed new solar arrays, and the vibrations would dampen after about 10 minutes after it came out of the shadow. So it was still useful. We could still do good science, but we were losing 15 or 20% of its observational capability. So we designed new solar arrays, took them up, replaced them, and it has taken some magnificent pictures. So that's the instrument we use. Now I'm going to move into the realm of the galaxies. But first I want to say just a little bit about our galaxy. We live within one. Here's a composite photograph of what's called the Milky Way. I hope it's dark enough that on an evening that we can go out. I brought my green astronomy laser, and we'll try to arrange with the crew a dark place so that I can show you some stars, planets, etc. But this is the Milky Way, with the center being in the constellation Sagittarius. We are a huge, huge galaxy, and it takes light 120,000 years to go from here to perhaps some other planet with a Hubble-like telescope over here. Let's talk about speeds and distances very briefly. A light year, the galaxies and the universe are so large we have to invent new yardsticks. One of our yardsticks is, how far does light travel in 1 year? The answer is a 6 followed by 12 zeros, miles, in 1 year, or 6 trillion miles. That's how far light travels in 1 year. Those numbers are so big. I worked with numbers like this for an entire career. I still don't understand 6 trillion miles, or 100,000 times 6 trillion light years for light to go from here to here. But here's the bottom line. The nearest star to us is 5 light years away from us, Alpha Centauri. We see it in the southern hemisphere. It takes light 5 years to go from its surface to us. So if it blinked out right now, how long would it be before we would know that it had blinked out? 5 years, exactly. As a comparison, the Earth is 93 million miles from the sun. It takes light 8 minutes to go from surface of sun to us. Jupiter, it takes an hour, hour and a half for light to go out to Jupiter. It takes 10 hours for light to get out toward Neptune. So our solar system is huge, even at the speed of light. One more analogy for you. When we send astronauts to the moon is 240,000 miles away, roughly 250,000 miles. At the speed of light, our radio signal to the astronauts who were circling the moon took 1 1/4 seconds to go 250,000 miles to the moon, and then when they replied, 1 1/4 seconds to get back. The largest rocket ever produced on the planet by human beings, the Saturn V, it took 3.5 days to send the astronauts from Earth to the moon. So light is the fastest thing that we know of, also a speed limit. In our galaxy, many of the large galaxies have this type of shape. Those of you who live in Florida and the Gulf Coast, if I took a picture of something from space that might be a weather phenomenon, what you might see something that looked like this. What would you call it? A hurricane. So the spiral arms of the hurricane that have all of the thunderstorms in them are the same physics or same phenomenon as these density gradients that come out and make these spiral arms. Why do we have spiral arms? We have what's called a supermassive black hole in the center of every galaxy. It is something that is so large and so massive that even light cannot escape from it. And what it does is it's the engine that drives this galaxy formation, and they're rotating, and out of that rotation come these spiral arms. We have 2 companion galaxies to the Milky Way. We generally do not see them from the northern hemisphere. They were discovered by a Persian astronomer in 964, and they're called the Large and Small Magellanic Clouds, named after Ferdinand Magellan, who circumnavigated the world in 1519, of course, had a beautiful view of them. Our next closest neighbor in terms of a galaxy is called the Andromeda Galaxy, and this is a beautiful Hubble photograph. It takes light from the Andromeda Galaxy, which is slightly larger than our galaxy, 2.2 million years to come from this galaxy to the Earth. Now imagine, how long have we been writing down human history? Anybody? Give or take 6,000 years, right? This morning Ian talked about they have found a Neanderthal skull in Gibraltar in one of the caves that is 50,000 years old. So if the Andromeda Galaxy has an event that we see right now, it happened 2.2 million years ago. An extraordinary large distance that these things have to cover. The other interesting thing I want to tell you is that we did not discover this formation of stars was an entire galaxy outside of our own until 1926. So look how far cosmology has come, our understanding of the universe, in about 90 years or so. We look in different wavelengths of light because we can infer different information. We take the light, we use a prism. What happens when you use a prism and you shine white light through it? What do you see coming out the other side? Anybody? A spectrum, and a spectrum says the white light contains all of these colors, and when I put it through a piece of glass of a prism shape, the speed of each color is very, very slightly changed, and that causes the white light to spread out into its spectrum, beginning at red and continuing through blue or violet. We look at these different wavelengths of light because we take the light from stars, we put it through a prism, we call it a spectrograph, and we can look at the atmosphere of an individual star, or I can look at the collective light of an entire galaxy, and I can tell what elements are in its atmosphere, because those elements absorb specific wavelengths or colors of light. So when we look at that light that came from an individual star, even in our own Milky Way, it's easier because they're closer. We can tell that it has hydrogen in its atmosphere, it has helium in its atmosphere, it has carbon in its atmosphere, it has oxygen in its atmosphere. And we classify stars based on the type of elements that are in them. This is the Andromeda Galaxy right here, looking in ultraviolet light. Notice the bright arms, the spiral arms are bright because they have very hot, very young stars burning their fuel. Any Eagles fans here? Eagles band? They did a great song called Life in the Fast Lane. And these stars are living in the fast lane, and they give out a lot of their light in ultraviolet, very powerful, the same stuff that burns our skin from sunburn. A wonderful woman astronomer, Henrietta Leavitt, lived in around 1900, was able to deduce what was called a new candle, a new yardstick. So let me make an analogy for you. If I were to come out here and I hold up your thumb, pretend your thumb is 1 candle power, and you measure 1 candle power, and you know that distance from me to you is 1 candle power, right? If I double my distance from you, what happens to this same 1 candle power? It's 1/4. It goes as 1 over the r squared. If I go 3 times further away, how bright is this candle to you? 1/9. So if I know that this is 1 candle power, and I measure its actual brightness with my telescope, I can deduce how far away that candle is by knowing that it originally was 1 candle power. It wasn't until the early 1900s that Henrietta Leavitt laid the groundwork that allowed us to use a specific type of star as a new yardstick, a new candle, and therefore deduce that that star that I measured in my galaxy, and knowing how bright it was, now if I saw that same type of star in a different galaxy, I could deduce the distance to the Andromeda Galaxy. The type of star for you is called a Cepheid variable. That will not be on the test, not to worry. The important thing is it changes brightness, and this graph represents brightness over a period of time. This can be months or it can be days. The period from maximum brightness to maximum brightness, when we measure that and plot that on a graph, I can tell if I measure that star's actual brightness with my telescope, and I measure how long between the peaks of brightness, I can deduce how bright it would be if it were right next to me, and therefore, when I measure its actual brightness, I can deduce how far away is the Andromeda Galaxy. And Edwin Hubble did exactly this in 1923. It took about 3 years before his theory was confirmed, and this is a revolutionary idea. This is the equivalent of, in the 1900s, there was a theory that the continents moved around, and that these continents moving around, crashing into each other, can create mountains. And it was an extraordinary theory and took decades before people actually believed it, that South America and Africa used to be connected, and that Europe and North America used to be connected, and they are now split in what's called the Mid-Atlantic Ridge. If you get to Iceland, Iceland is a hot spot on the Mid-Atlantic Ridge, formed by fire, sculpted by ice, and you can go to a part of Iceland and actually see this large canyon in the ground, not like Grand Canyon. You can walk in it, and that is where these two continents, Europe and the Americas, are splitting at about 3/4 of an inch per year. But my point is not to teach you about tectonics, but to teach you that radical new theories have to take some time before they can be proven. Edwin Hubble used the largest telescope at the time, 100-inch telescope, and he took these pictures. This is his actual picture right here in 1923, and in his writing, this star right here, he notes is a variable with an exclamation point, and he had found the first Cepheid variable, the new yardstick, and he was able to calculate that this large group of stars, previously we had no idea how far away it was 2.2 million light years from his telescope sitting right here. He was an extraordinary astronomer, also determined that the universe is expanding, and he was able to deduce that by seeing things in these far away stars, and their spectrum from their stars was changing because they're moving away from us. So Edwin Hubble did that. Now we took, and of course the Hubble Space Telescope is named for Edwin Hubble, and so we're thankful for that. And here is a picture of this actual Cepheid variable right here, taken with the Hubble Space Telescope, blown up 2010, December 17th, 21st, 30th, 26th. Notice what's happening to the brightness of this star. He was able to measure that and measure its period and deduce that this group of stars was an entire galaxy outside of our own. He classified galaxies. Here are some of the classifications. We think the Milky Way is this shape right here. These are various shapes. They have numbers that we still use today. And now I'm going to try to go to some magnificent Hubble photographs. One of my favorite. This is called the Whirlpool Galaxy. Right here is its supermassive black hole. Notice the magnificently formed spiral arms. What do you see about the colors here? Are they all the same? Of these stars? These stars are basically red, right? That means they're older, they burned up a lot of their fuel, and their surface temperature is much lower. Our sun is yellow or orange because its surface temperature is about 5,500 degrees centigrade. These red stars are about 4,400 degrees centigrade. The very, very bright blue stars, here would be an example, their surface temperatures can be up to 18,000 degrees, 3 times hotter than our sun. So they're burning their fuel at prodigious rates. That's a fancy rocket science word for big, fast, prodigious. They're burning their fuel very fast. So they live shorter lives. I love this one called the Sombrero Galaxy, discovered in 1767. These darker lanes are gas and dust that is not emitting light, but is actually blocking light from the supermassive black hole and all of its stars. And we are seeing this like a record that we're looking at the record on edge. This galaxy is the record turned so that we're seeing it in its frontal projection with its spiral arms. Of course, in a record, the spirals are a lot tighter, right? But it's the same principle. Are all of us old enough to remember records? 33? I know I am, but you know, now it's become a novelty to still have something that will play those boxes of records that I have in a closet. And then the beautiful NGC, National Galactic Catalog. Another one, 61 million light years away. Remember, Andromeda was 2.2 million. This is a beautiful barred spiral. There's something about the magnetic field and the unique rotation of this supermassive black hole that causes it to make a bar, and then the spiral arms start. Every galaxy is unique. Notice this one has a lot of very young, hot, blue-white stars. Also notice in the center, this yellowish light means these are older and cooler and newer, brighter stars in the spiral arms. What's interesting about this is in this Hubble photo are what are called quasars. These are objects that are so far away, they are billions of light years away. And we believe that they were very important in the early formation of the universe before it had expanded to its size now. Very, very important in the formation of these supermassive black holes that later in the evolution of the universe became the galaxies that we see. Spiral galaxy M74, it's a grand spiral, meaning it has inside here, if I were to change this light resolution, it's a little bright, but you can see the inside this one is a very tight spiral, then the big spirals coming out. But they're just absolutely beautiful. One of my favorites, the Pinwheel Galaxy, N101. This is what we used to hold outside of our cars in the 50s and our mothers, so that little pinwheel thingy. And when Dad was driving down the road toward Niagara Falls, and Mother would go nuts because our hands were outside the car window, right? And the Pinwheel Galaxy, absolutely beautiful. Look at the symmetry of the arms, and the formation looks just like a pinwheel. There are very active galaxies. This one is called a starburst. The galaxy, the supermassive black hole, is spinning inside of this galaxy, and the stars are spinning with it, and it causes a rotation of these arms and stars. But along its spin axis, it is somehow spewing out material along that axis that is creating these bursts of stars. So these two objects are at the same distance and are related to each other. This one is in the Big Bear, Ursa Major, called the Cigar Galaxy because this looks like a cigar. Bode's Galaxy, 11 million light years away, is another very, very beautiful active nucleus. Its supermassive black hole is 70 million times the mass of our sun. We think the black hole inside of the Milky Way is around 4,500 solar mass, 4.5 million. So this one is much, much bigger. This galaxy is called backlit because the light is coming from behind it and through the dust and gas and spiral arms, and gives us this magnificent color and gives us special information. When I talk about the solar system, I want you to remember the term backlit. I'm going to show you a picture of Saturn and its rings from a spacecraft on the opposite side of Saturn, where the sun's light is coming through the rings, and is a spectacular photograph, and this is the same concept. When we look in ultraviolet light, notice now we're looking at the younger, very hot, very active stars. So the shapes will be different depending on the wavelength, which represents energy of light. Ultraviolet, more energy. Younger galaxies we think look like this. As they get older, become like this, start losing their spiral arms, transition, and then become old and yellow or reddish galaxies. Now I want to switch subjects, and I want to talk to you some about interaction of galaxies, which is another extraordinary group of photographs. And this one looks like Frank Sinatra's hat, right? This used to be in the same plane as a record, but it has had a gravitational interaction with another galaxy that has swung by it and bent the brim, or bent the record, bent the rim, and changed the shape as one galaxy interacts with another. This is just the beginning of what we see with interacting galaxies. One of my favorites called Stephan's Quintet. That means 5 different galaxies. This galaxy swung by this galaxy, and notice what happened. These used to have spiral arms like this in earlier photographs, but the spiral arms have now become distorted from the tidal interaction. So what's a tidal interaction? What happens to the oceans on the Earth as the moon goes around the Earth and the Earth rotates? There's something happens to the water. We call it what? Tidal motion. The gravitational pull of the moon is attracting the water a little bit more on the side that the moon is of the Earth's oceans than the opposite side, and it causes the tides twice a day as the Earth rotates. Same thing happens when one entire galaxy swings by another. That gravitational force can now change the shape and the orbits of these stars. All of this, young blue stars, comes from the gas and the density, and the change in these orbits has formed new stars where no star existed because I have changed their shape. And we see that every time we see tidally disrupted galaxies. This galaxy went right through the spiral arms of this one from right to left. Millions and millions of years it takes for these phenomena to play out. But look what happened, how it destroyed the spiral arms, but it created new star formation and new planets in a completely different area of these galaxies. So these tidal gravitational interactions of galaxies swinging by each other create new stars. The same image of the Cartwheel galaxy, we're looking at 3 different colors of light. The blue is from the Galaxy Evolution Explorer, which looks in ultraviolet. The green is from the Hubble Space Telescope, which sees light that we see. And the red is from the Spitzer Space Telescope, which is looking at infrared, lower wavelengths that our eyes don't see. And the purple comes from X-rays, which are very, very powerful. And we put all of that together, modern digital wizardry, and we can now learn a lot more about the structure and the age of the different stars in these galaxies. Hoag's object, which is extraordinary. What happened to its spiral arms? We're not sure. But what's interesting, these are very, very rare. But in this Hubble photo is another object with the same shape inside this outer ring that is far, far away from this one. So we see this one in the foreground, this one in the background. We are not sure what would cause this beautiful circle that now no longer has the spiral arms. Notice the disruption of this galaxy, which used to have spiral arms, and these are new stars that interacted tidally with this galaxy as it swung by. Here's an even better example. This is the one galaxy that has been completely ripped apart. It's the smaller one, but it was large enough to disturb the spiral arms. In this case, think of our record as now being opened up like a couple of pages together. So it's no longer in the same plane, but has actually taken the spiral arm out of the plane of the original galaxy, called the Tadpole Galaxy. Have you noticed that astronomers tend to give names to objects that, that really doesn't sound real scientific, does it? Tadpole, but that's what a tadpole looks like. One of my favorites, called the Rose. This smaller galaxy has been entirely deformed as it swung by the larger galaxy above. See how it has distorted the spiral arms? These are the petals of the rose with these beautiful blue, brand new, hot, young stars up above it, and here's the stem. of the rose. This looks like some of our 4th of July fireworks where these two galaxies, this one has been completely torn apart and now looks almost like a bridal veil. These used to have a symmetric shape. So we're seeing with Hubble, as we see further and further away and more clear pictures, we're seeing more evidence of these interaction between galaxies that significantly change their shape. And when we deduce when this happened, we see more of these happenings early in the formation of the universe when the galaxies were closer together. And as we have expanded over 14 billion years, give or take, the galaxies are further apart and we don't see these interactions as often. So with the Hubble Space Telescope, we really have a time machine to look backwards in time, which is further away from us, and see how, and begin to try to understand how is the universe changing in size, in shape, in content. Another example, these are called the antenna galaxy. What I've done here is a large, big picture. These two galaxies right here have interacted. Here's the supermassive black hole of one, the center, the other, and then Hubble has blown up this area and made a composite picture of the inner form of these galaxies. We believe after an interaction that was this close, these two supermassive black holes have captured each other, will continue to rotate. They give off energy over periods of time. They will get closer and closer together and then merge into a huge, huge supermassive black hole, the sum of the two masses of the two individual ones, and then later may begin this new galaxy structure with spiral arms. Still working on that. This is a great picture. I love this picture. I got to tell you a little story. Hubble Space Telescope time is very, very valuable, and there's a large team of people that at the Goddard Space Flight Center that schedule the different types of scientific observations on this very valuable resource. And what they're looking for, you have to put in a proposal. What is it you want to use Hubble for? Why is that important? Understanding what you're going to see. What are you looking for? One of the proposals that came in was we look at a piece of sky, pretend you have a straw right in front of your eye, a drinking straw, and you look up in the sky, you're seeing a very, very tiny piece of the sky, correct? Through the straw. Through your straw with your naked eye, you see absolutely nothing. It is completely dark. Through telescopes on the ground, we look at that same tiny piece of sky, we see nothing with telescopes. One of the proposals came in and they said, guys, we want to look at this tiny piece of sky that has nothing in it in the constellation Fornax, and we want to use the Hubble for the equivalent of a 23-day time exposure. 23 days of Hubble time to look at nothing. How long do you think that meeting was? Before they finally went, okay, I give up, go ahead and do it. When they did it, with our brand new wide field camera number 3, the most sensitive camera put up on the Hubble Space Telescope in 1998, we developed that film. You don't develop film. You take a digital image, you store it in a computer. You come around the next time, then you look at that piece of sky and you keep piling up this information into one photograph. This is what we found when we looked with ground-based telescopes that saw nothing. There are 10,000 galaxies with this long time exposure that were so dim we saw nothing with ground-based telescopes. You put all that together, here's what Hubble saw. An extraordinary finding. Here's a blow-up of some of these galaxies. When we can look at their light, blow their light up and tell that they are far, far away. These are billions and billions of years ago. I'm looking back in time, 2/3 in the past of the age of the universe, whatever that is. Another thing that we found with Hubble, there are large clusters of galaxies, and they seem to have formed in this cosmic web after what's called the Big Bang, something we don't understand. From nothing came this Big Bang and this huge amount of energy that has been expanding for 14.5 billion light years. We can see, we predicted its initial signature of what we should see from this explosion if it happened. We've measured that in the 1960s with the first radio telescopes. They had no idea what it was, and it turned out to be the ancient signature of this explosion. But if you look at high-speed photography of explosions, what you see are these lines or webs where there are higher densities of materials. It's not just continuous molecules. And what we find is there are large structures of huge numbers of galaxies that form along these lines of higher density material. We look at our largest galaxies, what's called our local group. Here's the Milky Way. Here's Andromeda, 2.2 million light years away. Here's 1 million light years, and we can see all of these groups called our local group seem to be gravitationally bound together and have formed in one of these earlier filaments. We've even discovered much larger. Here's our local cluster. This is called the Virgo supercluster, and even larger, this is 90 million light years in 3 dimensions. And what this is telling us is something about this filament structure that we can better understand how the universe even came into existence. I mentioned the Virgo supercluster. This beautiful Hubble photographs, what they've done is taken out digitally individual stars so that we can expose this for a longer period of time. And these are the magnificent, all of these Virgo supercluster of galaxies. We might be, I don't know which ones we are, but we would be something like here, and here's Andromeda. But all of these are related, and they seem to be gravitationally bound and moving and changing. One last slide for you. You thought I was going to talk about astronomy. And my last name is what? What type of bird do you think of when you hear buzzard? Anybody? What type of bird? Scavenger. Vulture, right? Vulture. Only in North America am I considered a vulture. The truth is, the common buzzard is the head of family of all broad-winged hawks. Is not a vulture. I spent an entire youth in school as a boy named Sue. Anybody Johnny Cash fans? So, in this, I had to have just one little advertisement. This is actually the common buzzard in Scotland, common throughout Europe. No one in Europe makes the mistake that a buzzard is a vulture. They know that they are a large, broad-winged hawk. So, with that, I have a couple of minutes for a few questions and would be happy to take any of your questions. I'll try to repeat them for you so the others can hear right here. Yes, sir.
If the Milky Way collided with Andromeda, would we know it?
Okay, the question is, if the Milky Way collided with the Andromeda, would we know it? So let me give you, I can't answer that question. We think that it's so far in the future that you and I won't know it, but if there are still humans on Earth, it will be an unbelievable and spectacular event. Our humans, as we know them, probably won't survive because it'll throw stars everywhere. It'll completely disrupt our solar system. And in fact, it's a good question because Andromeda is the only galaxy that is moving toward us. All the other galaxies we see are moving away from us. And we know that by measuring the light waves from Andromeda. And think of it this way. When you hear a train coming toward you, blowing his whistle, is the sound higher or lower when he's coming towards you? Okay? When he goes past you directly, it's the actual pitch of the whistle, correct? And when he's going away from you, receding, the pitch is lower. Light does the same thing. We can measure hydrogen atoms. Its electrons have a unique signature that we see throughout every time we see hydrogen. These four famous lines of the Balmer series of hydrogen atoms recombining, giving off specific frequency of light. If it's moving toward us, they're shifted to the blue or higher frequency, but the distance between the four lines stays the same. If it's moving away from us, these hydrogen lines are shifted to the red. And so it's very similar to the Doppler effect, and we can measure the rate and how we are moving with respect to another galaxy. Andromeda is moving toward us. It's hundreds of billions of years, we think, or millions of years before it actually impacts with us. But when that happens, you will see those colliding galaxy pictures of the Milky Way and Andromeda will be dramatically changed in their shapes. Their spiral arms will be torn apart. Question right here, yes, sir.
If the black holes are negative matter, how do they throw off positive matter into the spiral arm?
Okay, the question is, if black holes are negative matter, how do they throw off positive matter that we can see? The first thing that we don't know what's inside of a black hole. We think it is positive matter. Its mass is so large, its gravitational field so strong that it's still positive matter inside, but it can't emit any light or information. So it's not negative matter. Now, the answer, we're not completely sure, but around its spinning axis, pretend I'm spinning like a top, okay? So my axis is my head and my feet, right? The black hole spinning like this, its spiral arms are out here where my arms are, but out of my head and feet, it can eject matter for physics we don't understand, still to be learned, and it can come out away from it and create those starbursts, which are extraordinary events. A lot more to learn about black holes. Anybody over here? Right there, yes, sir.
The quotation you have from Scripture there, the heavens declare the glory of God. Define God in that context.
In that context, this is a scripture from the Bible, the Old Testament, and it's the same context that I would do, that God is my creator. That would be my definition. What would yours be? Okay. Anybody else? Right here, yes, sir. And then over here.
The galaxies, most of the pictures, they all seem to be spinning in
Yes.
the same direction. Or is it also
Well,
just like southern hemisphere and northern hemisphere here?
So your question is, are they spinning in the same direction? We don't know. Actually, spinning in the same direction depends on where I am with respect to looking at it. We have what's called the right-hand rule in physics, right? Angular momentum and other stuff is conserved. So if I'm above it, it's spinning counterclockwise. If I'm below it, it's spinning clockwise. Now, I think your question is, are all of these spin axes in the same orientation? The answer is no. However, we've recently discovered, if you remember that little filament slide, we've recently discovered that these galaxies in the filaments seem to be spinning perpendicular to the line of the filament. So it has something to do with helping the formation and establishing the spin axis. Good question. Over here, there was a question. Somebody over here? I heard a voice. Okay, go ahead.
I'm going back to
To where? The unmoved movers? That's the greatest question that none of us could answer. That's the truth. How can something come from nothing? And that is why we're sending all these telescopes and things out there to try to understand and answer that question. We have no answer for that. I wish I knew. Question.
The expected lifespan of Hubble from this point forward, and what options are there to replace it?
Okay, what's the expected life plan of Hubble from here forward, and what are the options to replace it? Great question. We don't know on Hubble. Its last mission was 10 years ago, give or take. 7 years ago, I guess, 98, this 2015. Hell, I can't even do science, that's 12. 17, sorry. We're going to use it as long as everything is functioning. Right now, there are only some minor things that have failed. It's still functioning well. The other thing I would say to you is, since the space shuttle is retired, we now have no capability to go back and repair Hubble. So once Hubble breaks, unless we develop something like a space shuttle, remember a space shuttle has the garage that you can work on your car. It has the tools inside your garage that the astronauts do. It has an airlock like a submarine so that you could put your spacesuit on and go out into the garage, which is vacuum, inside the cargo bay and work on it. So we are losing extraordinary capability to repair things because we no longer have a space shuttle. What replaces it will be what's called the James Webb Telescope. Much larger, much more capable, will be launched with an expendable rocket probably 5 to 7 years from now. It's in testing. It's all the time I have for you, and I hope to see you on the ship. Any of you, we will be joining people for dinner. Anytime you catch me, feel free to ask me a question. Happy to do that. That's why I'm here. Have a great trip, and say thank you to our wonderful crew on the lovely Seaborn Odyssey. Thank you.